Today we will study recurrence relation. So first of all, what is a recurrence relation? A formula which expresses any term of a sequence as a function of its previous term is called recursive. And the relation is called the recurrence relation. For example, the nth term an of the sequence 3, 8, 13, 18, 23 may be written as an equal to an minus 1 plus 5 for n equal to n greater than equal to 2 and a1 equal to 3. Because a1 is 3, so if we and n is greater than equal to 2, if we substitute n equal to 2 here, we get a2 equal to a1 plus 5 and a1 is 3 here, 3 plus 5 is 8. a2 is a1 plus 5. a3 is a2 plus 5. a2 is 8, so a3 is 8 plus 5 equal to 13 and so on. So this formula is called the recursive formula and this relation is called the recurrence relation. And this equation is also called the difference equation with initial condition a1 equal to 3. Now what is the order of this recurrence relation? The order of recurrence relation is defined to be the difference between the highest and lowest subscript of an. If we have the recurrence relation an plus 5an minus 1 plus 3 equal to 0, here the highest subscript is n and lowest subscript is n minus 1 and difference between n and n minus 1 is n minus n minus 1 is 1. So order of this recurrence relation is 1, or we say that it is a first order recurrence relation. In second example, highest subscript is an, lowest subscript is n minus 2, difference between highest and lowest subscript is 2. So the order of this recurrence relation is 2, or we say that it is a second order recurrence relation. Now the degree of the recurrence relation. The degree of recurrence relation is defined to be the highest power of an or fx. The degree of recurrence relation an cube plus 3 an minus 1 square plus 2 an minus 2 equal to 0 is 3 because power of an is 3 here. And the degree of an plus an minus 1 plus an minus 2 equal to 0 is 1 because here the power of an is 1. So the degree is the highest power of an or fx if the recurrence relation is given in terms of fx. A recurrence relation is called linear if it is of degree 1. It is called quadratic if it is of degree 2. It is called cubic if it is of degree 3 and so on. Now what is homogeneous recurrence relation? A recurrence relation is called homogeneous if it contains no term that depend on the variable n. Otherwise it is called non-homogeneous. Now we will discuss a method to find the solution of homogeneous recurrence relation. So first of all, suppose we are given a recurrence relation C0 an plus C1 an minus 1 plus C2 an minus 2 plus Ck an minus k equal to 0. Here C1, C2, C3, Ck are all different. So first of all, we will make characteristic equation of this difference equation or recurrence relation. So for this, we will substitute an equal to a raised to power alpha n. Then we will find the roots of characteristic equation. Suppose the roots of this characteristic equation are alpha 1, alpha 2, alpha 3 and so on. This is alpha 2 here. Now there are three cases of roots. Number 1, when roots are distinct. If roots are distinct, then we have the solution of the form a1 alpha 1 raised to power n plus a2 alpha 2 raised to power n plus ak alpha k raised to power n. If the roots are equal, suppose alpha 1 is the characteristic root of the equation which is repeated m times. Then the solution is an equal to a1 n raised to power m minus 1, a2 n raised to power m minus 2 plus am n raised to power n minus m alpha 1 raised to power n. For n in some books, the notation is r also. So you may use any notation, but the solution of the characteristic equation, if the roots of characteristic equation are repeated m times, then the solution of recurrence relation will be of this form. But if roots are complex, in that case, we have an equal to gamma raised to power n a1 cos n theta plus a2 sin n theta. And we can calculate gamma and theta by using alpha plus iota beta equal to gamma cos theta plus iota sin theta, where alpha plus iota beta is the complex root of the characteristic equation. And we know that complex roots always occurs in conjugate pairs. Therefore, alpha minus iota beta is gamma cos theta minus iota theta. So, using these two, we can calculate the value of gamma and theta. Like we can solve this equation and find the values of gamma and theta. So, we have discussed all the three cases. When the roots are distinct, then the solution is of this form. If the roots are repeated m times, then solution is of this form. When the roots are complex, then solution is of this form. Now some examples. First of all, we find the solution of the recurrence relation an plus 1 minus 1.5 an equal to 0 where n is greater than 0. So to solve this equation, we substitute let an is equal to a alpha raised to power n. If we replace n by n plus 1 here, we get a n plus 1 equal to a alpha raised to power n plus 1. We have replaced n by n plus 1, n by n plus 1. If we substitute these two in the given equation, an plus 1 minus 1.5 an equal to 0, then we get a alpha n plus 1 minus 1.5 a alpha n equal to 0. And this implies if we take a common, also alpha n is common in both the terms. So if we take a alpha n common, here we are left with alpha raised to power 1, which is alpha. Here we are left with 1.5. But a alpha n is not equal to 0. It means alpha minus 1.5 is equal to 0 or alpha equal to 1.5. It means the solution of homogeneous recurrence relation is given by, we had substituted an equal to a alpha n, and here alpha is 1.5, so an is equal to a 1.5 raised to power n. So this is the solution of given recurrence relation. Suppose one more example, we find the solution of recurrence relation an equal to 5 an minus 1 minus 6 an minus 2 n greater than equal to 2 with initial conditions a not equal to a1 equal to 3. We can write this recurrence relation as, if we shift these two terms to left hand side, so then we get an minus 5 an minus 1 plus 6 an minus 2 equal to 0. If we substitute an equal to a alpha n, then if we replace n by n minus 1, then we will get an minus 1 equal to a alpha n minus 2. If we replace n by n minus 2, an minus 2 equal to a alpha n minus 2. If we substitute all the three values of an minus 1, an minus 2 in the given equation, we get an is a alpha n, so a alpha n minus 5, an minus 1, so a alpha n minus 1, a plus 6 an minus 2 plus 6 a alpha n minus 2 equal to 0. If we take a alpha n common in these terms, then a alpha n, here we are left with 1 minus 5, a alpha n is common, So we are left with alpha raised to power minus 1. Here a alpha n is common. So we are left with 6 alpha raised to power minus 2 equal to 0. But a alpha n cannot be 0. Therefore 1 minus 5 alpha inverse plus 6 alpha raised to power minus 2 is equal to 0. And if we multiply this equation by alpha square, then we get alpha square minus 5 alpha plus 6 equal to 0. If we factorize this, because 3 2s are 6 and 3 and 2 are 5, alpha minus 2 into alpha minus 3 equal to 0. It means alpha equal to 2 and alpha equal to 3 are roots of this characteristic equation. Alpha square minus 5 alpha plus 6 equal to 0. This is the characteristic equation. Here the roots are real and distinct. Now the solution of homogeneous recurrence relation is given by an equal to a1 alpha 1 raised to power n plus a2 alpha 2 raised to power n, which we had discussed here. An is equal to a1 alpha 1 raised to power n plus a2 alpha 2 raised to power n plus ak alpha k raised to power n when the roots are distinct. So here we have two roots and these are different, so we get this value. If we substitute alpha 1 equal to 2 and alpha 2 equal to 3, then we get a1 2 raised to power n plus a2 3 raised to power n. But we are given some initial conditions, means a naught equal to 3 and a1 equal to 3. A naught equal to 3 means for n equal to 0, the value of an is 3. For n equal to 1, the value of an is 3. So if you use these initial conditions and if we substitute n equal to 0 here, then we get a naught equal to a1. N equal to 0 means 2 raised to power 0, which is 1. 3 raised to power 0 means 1. So here a naught equal to a1 plus a2. But a naught is given to be 3 here. So it is a1 plus a2 equal to 3. Now for n equal to 1, a1 is equal to a1 2 raised to power 1 plus a2 3 raised to power 1. But a1 is given to be 3. So it means 2a1 plus 3a2 equal to 3. This is a value for n equal to 1. These equations are easy to solve. We can multiply this upper equation by 3. If we multiply this upper equation by 3, we get 3a1 plus 3a2 equal to 9. If we subtract the two, 3a1 minus 2a1 is a1. 3 3s are 9 minus 3 is 6. So we get a1 equal to 6. So I have skipped the calculation work here because you can easily solve this equation. To get the value of a2, we can multiply the upper equation by 2. So you will get 2a1 plus 2a2 equal to 6. So if we subtract the two, these two will cancel out. 2a2 minus 3a2 is minus a2. 3 2s are 6 minus 3 is 3. So it means a2 equal to minus 3. So we have obtained a1 equal to 6 and a2 equal to minus 3. If we substitute these values in this relation, we get an equal to 6 2 raised to power n, a1 is 6, minus 3 3 raised to power n, a2 is minus 3. So this is the solution of given recurrence relation. So this is the case when roots are real and distinct. Suppose we find the solution of the recurrence relation an plus 6 an minus 1 minus 11 an minus 2 plus 6 an minus 3 for n greater than or equal to 3 with initial conditions a naught equal to 2 and a1 equal to 5 and a3 equal to 50. This given recurrence relation can be written as, if we shift the terms on the right hand side to left hand side, we get an minus 6 an minus 1. If we shift this side, plus 11 an minus 2, shift this side, minus 6 an minus 3 equal to 0. If we substitute an equal to a alpha n, if we replace n by n minus 1, we get a n minus 1 equal to a alpha n minus 1. If we replace n by n minus 2, a n minus 2 equal to a alpha n minus 2. Then we get a alpha n. We are substituting in this equation. A n is a alpha n minus 6. A n minus 1 is a alpha n minus 1 plus 11. A n minus 2 is a alpha n minus 2. Then minus 6 a. So it is n minus 3. So if you replace n by n minus 3, we get a alpha n minus 3. So it is 6a alpha n minus 3 equal to 0. If we take a alpha n common here we are left with 1. Here it is minus 6. It will be 6 here. A alpha raised to power n common, alpha raised to power minus 1 plus 11, alpha raised to power minus 2. A alpha n is common. Here it is minus 6. It is 6 here. So it is a typing mistake. So here it is, here we are left with alpha raised to power minus 3. If we multiply, this is 6 and this is also 6. If we multiply this equation by alpha cube, we get alpha cube minus 5. It was 6 here, minus 6 alpha square plus 11 alpha minus 6 equal to 0. Because a alpha n cannot be 0, so this term is equal to 0, and on multiplying it by alpha raised to power minus 3, we get this equation. Now we can easily factorize this equation, and the factors of this equation are alpha minus 1, alpha minus 2, alpha minus 3 equal to 0. It means this equation has 3 roots, 1, 2 and 3, and all the 3 roots are distinct. So we write alpha 1 equal to 1, alpha 2 equal to 2 and alpha 3 equal to 3. So the solution of given homogeneous recurrence relation is given by an equal to a1 alpha 1 raised to power n, a2 alpha 2 raised to power n plus a3 alpha 3 raised to power n. If we substitute alpha 1 equal to 1, alpha 2 equal to 2 and alpha 3 equal to 3, we get a1 1 raised to power n plus a2 2 raised to power n plus a3 3 raised to power n. But we are given some initial conditions. First is a2 equal to 2 for n equal to 0, a0 is 2, for n equal to 1, a1 is 5, for n equal to 3, a3 is 15. So if we put n equal to 0 here, so a1 n equal to 0 plus a2 n equal to 0, a3 and a0 is 2. So it is 2 here. If we substitute n equal to 2 here, so sorry, first we will substitute n equal to 1 here. So it is a1 1 raised to power 1 means a1, a2 2 raised to power 1 yani 2a2, a3 3 raised to power 1, yeah. So this is 3a3 and this a1 is 5. Here it is given. So it is a1 plus 2a2 plus a3 is 5. For n equal to 2, we get a2 equal to a1, 1 raised to power 2, it is again 1, a2 2 raised to power 2 means 4, a3 3 raised to power 2 means 9, a1 plus 4a2 plus 9a3 and a3 is 15, so it is 15. We are the value is already given to us. So these equations are easy to solve. If we solve these equations, we get a1 equal to 1, a2 equal to minus 1 and a3 equal to 2. If we substitute these values in this equation, then the solution is an equal to a1 is 1, so 1 raised to power n is 1, a2 is minus 1, minus 1 2 raised to power n, a3 is 2, 2 raised to power 2 3 raised power n. Now we will solve one more recurrence relation, an plus 2 minus an plus 1 plus an equal to 0 with a naught equal to 1 and a1 equal to 1 plus under root 3 upon 2. So if we again substitute like this equation, an equal to a raised to power alpha n, an minus 1 equal to a raised to power alpha n. This pattern is used in every term, and like here after substituting, we take a alpha n common and simplify it and then multiply by alpha 3. These steps are common in all the examples. Then we get this characteristic equation, alpha cube minus 6 alpha square plus 11 alpha minus 6 equal to 0. So here in this example, I have directly written the characteristic equation alpha square minus alpha plus 1. If we will substitute an equal to a alpha n and an plus 1 equal to a alpha n plus 1, then we get this characteristic equation. If we solve this equation, we get alpha equal to 1 plus minus iota root 3 upon 2, because this equation can be compared to ax square plus bx plus c equal to 0, and using Sridharacharya method, here a is 1, b is minus 1 and c is 1, and according to Sridharacharya method, x is equal to minus b plus minus b square minus 4ac upon 2. So minus b means minus into minus 1 plus minus iota b square minus 4ac, 1 square minus 4 means minus 3, under root minus 3 is iota root 3 upon 2a means 2. So alpha comes out to be 1 plus minus iota root 3 upon 2. Here in this case, the roots are complex numbers. If the roots are complex number, then the solution is of the type an equal to gamma raised to power n, a1 cos n theta plus a2 sin n theta, which we have discussed in second slide. So to find the values of gamma and theta, we compare it alpha equal to gamma e raised to power iota theta, or we can write it as gamma into cos theta plus iota sin theta. This we have already discussed, and this is the root 1 plus iota root 3 upon 2. If we compare the real and imaginary part, then we get gamma, here it is gamma cos theta, real part, here it is 1 by 2. Real part is 1 by 2. Here the imaginary part is gamma sin theta, here the imaginary part is under root 3 by 2. It means gamma cos theta equal to half, gamma sin theta equal to root 3 by 2. It means if we square and add gamma cos square theta plus gamma sin square theta, take gamma common, cos square plus sin square theta is 1. So we are left with gamma square this side, and if we square and add this, 1 upon 4 plus 3 upon 4. So means 1 by 4 plus 3 upon 4 is 1. So it means gamma is 1. If we divide these two, gamma sin theta upon gamma cos theta, it is tangent theta, because gamma will cancel out, and under root 3 upon 2 upon 1 upon 2, it is under root 3. So gamma equal to 1, tangent theta under root 3 means theta is pi by 3. Then the solution of recurrence relation is given by substitute the value of gamma and theta here. Gamma is 1 raised to power n, a1 cos n pi by 3 plus a2 sin n pi by 3. Now initial condition is a naught equal to 1. Means when n is 0, then a naught is 1. For n equal to 0, substitute here, a naught is 1, n equal to 0, cos 0 is 1, a1, n equal to 0, sin 0 is 0. So this is, so it means a1 is 1. If you substitute n equal to 1 here, a1 is 1 plus root 3 upon 2. So it is 1 plus root 3 upon 2. And a1 here, n equal to 1 here, so here it is and n equal to 1, 1 raised to power 1 is 1, a1 cos pi by 3. Cos pi by 3 is 1 by 2. 1 by 2 a1 plus a2 sin pi by 3. Sin pi by 3 is root 3 by 2. So half a1 plus root 3 by 2, a2 is equal to 1 plus root 3 upon 2. If we compare the corresponding terms, then half of a1 is equal to 1 by 2, means a1 equal to 1. And under root 3a2 is equal to root 3 by 2. Under root 3 upon 2 will cancel out from both sides. We get a2 equal to 1. So the required solution is an equal to 1 raised to power n cos n pi by 3 plus sin n pi by 3. We have substituted the value of a1 and a2 here. a1 and a2 both are 1. So an is 1 raised to power n cos n pi by 3 plus sin n pi by 3. Thank you.